Okay, in the previous video, we saw that we could get an upper bound on the error for the square root of 18 by applying this formula that we talked about. Looks like this, and so we found that f of 18, and this is using the function f of x equals square root of x, and the cubic polynomial estimate centered at x equals 16. So that's our value of a. So what we found with the theorem was that f of 18 minus the cubic polynomial at 18, this would be the absolute error between the estimate and the actual value, is no more than, this is what we mean by an upper bound on the error. The error is no more than m times 18 minus 16 to the fourth over 4 factorial. So just make sure you understand where all these variable assignments are coming from. X is where we're evaluating everything, so that's 18. A is the center of the approximation, that's 16. N is the degree of the polynomial we're using to do our approximation, that's 3. And the m here is the only thing that we have to figure out. We did that by drawing a picture of the next derivative, so the fourth derivative. We used up to the third derivative to build P3, and so the fourth derivative would be the next one. We found that taking m to be 0.00006 would be good enough. That number is greater than or equal to the fourth derivative at x. Well, I guess I used a different letter. It's bigger than the absolute value of the fourth derivative at c for all c between 16 and 18. So in other words, between the x and the a, the point of the approximation and the center of the approximation. So that's what the m is, and we got that by looking at a graph of the fourth derivative and only paying attention to the region between 16 and 18. Okay, so let's apply that same idea to some other problems. This one is one that we did not actually do an approximation for on day 2, but this is one of the ones that we did write the polynomial for. I think this was the one that you did for the day 1 homework. So this was the table using log of x and its first and second derivative, and we're centering this approximation at 1 here. And so the polynomial, here we're using the second degree polynomial, approximation will be 0 plus 1 over 1 factorial, x minus 1 minus 1 over 2 factorial, x minus 1 squared, which can be simplified as x minus 1 minus 1/2 x minus 1 squared. So this will be my my approximating polynomial. The estimate that I would get for 4/5 then would just be 4/5 minus 1 minus 1/2 of 4/5 minus 1 squared. And so it'll be 1/5 minus 1/50th, negative 1/5 minus 1/50th. So that's negative 11 over 50, negative 0.22. In fact, it's exactly negative 0.22. So that's the approximation of the log of 4/5. So I'm saying log of 4/5 is approximately negative 0.22. The error, the absolute error, would be the absolute value of the difference between these two. So an absolute value measuring the difference. And the theorem says, without actually being able to compute a log, I can use the theorem, and it says that this will be no more than the formula written out using x is 4/5, a is 1, and n plus 1 is 3. Since our approximation was the second degree polynomial, our n here is 2. And so I need to know what is the m. So m needs to be at least as big as the absolute value of the third derivative ever gets for values of c between 4/5 and 1. In other words, between where we're making the approximation and where the center of the approximation is. So I can go look at my graph. My center of my graph is at 1. I'm making the approximation at 0.8. So all I care about is this part of the graph. And on that part of the graph, the furthest this graph ever is away from the x-axis is right over here. And if you look closely, 4 is a little bit above the graph, above 0.8. So I could use m equals 4 in the error formula, and that would work fine. If it's hard to tell, just use m equals 5. It really doesn't matter. Your m should be the right order of magnitude. In other words, shouldn't be 1,000,000 just because that would definitely be bigger. So it should be something on the graph. But if you really can't tell, just pick the next nice number to work with above where you think it is. And so this error bound then would be 4, 1/5 cubed would be up top here, and 3 factorial would be right there. And so the upper bound of my error is going to be 0.0053. So when I use this approximation for log of 4/5, the most that I could be wrong is 0.0053. That's the most error I could have in that approximation. So the real error in the approximation is no more than 0.0053. All right, one more. I wanted to do one that used the cosine approximation just because there's something special about sines and cosines that we can take advantage of, and that is, oh, I never did say what that derivative was, did I? Yeah, sorry. This derivative is 2 over 2x minus 3. So that's, I do need that third derivative. That is a graph of that, y equals 2x to the minus 3. So just FYI, that's what that graph is of. The graph is of the third derivative of the original function there. All right, so here I need the fifth derivative of the cosine function, but cosine's derivatives are dumb. They just alternate between sines and cosines. And so, so I can just note that the absolute value of the fifth derivative is always less than or equal to 1. And that's because sines and cosines outputs are always between -1 and 1. So the absolute value of the fifth derivative is definitely less than or equal to 1 no matter what values of c you're using. And so that means when our function is something like sine or cosine, we could just use 1 for m, and we know that that'll be okay. That may not be a great choice for m. We saw above that we can be a little bit off from reality and still not be too far away. So m equals 1 might be overstating the error a little bit. But again, it's supposed to be an upper bound on the error. So it's fine. If you write something down that's bigger than it needs to be, that still is an upper bound on the error. Anyway, so in this case, when I use the P4 approximation of the cosine function, which we figured out last time what the absolute error was for that, but the theorem says that's no more than m, which is 1, times 1 minus 0 to the fifth over 5 factorial. And again, the idea here is that x is 1. That's where we're evaluating the polynomial. A equals 0. That's the center of the approximation. N is 4. The degree of the approximation is the fourth degree approximation, which is why I have n plus 1 is 5 in this formula. And I'm using m equals 1 because the absolute values of sines and cosines are always no more than 1. So if I do this calculation, I just have 1. It's basically 1 over 5 factorial. And so that is 0.0083. So in the approximation that we did last time of P4 at 1 instead of cosine of 1, the theorem tells us that that approximation has to be within 0.0083. And if you go back and review the absolute error that you got, you'll see that it's quite a bit less than that. The reason that this upper bound is overstating the error a little bit is precisely because I'm being lazy here and not even looking at a graph of the fifth derivative. I'm just saying, well, 1 is definitely big enough. And there's nothing wrong with that, but that means that, that this error will be overstated just a little bit. But it certainly is correct.